In this video, I'm going to talk about something called the Nernst Equation in electrochemistry and an application of the Nernst Equation to a chemical problem. Okay, so we've already covered a couple of relationships. One is that the Gibbs energy is equal to minus the number of electrons transferred times the Faraday's constant times the voltage E. So the other equation was from the previous chapter in thermodynamics, and that is the Gibbs energy is equal to the Gibbs energy of the standard state, delta G naught, plus the gas law constant in joules, if these are in joules, times the Kelvin temperature times the natural log of the reaction quotient. Okay, so what we'll do is we'll take delta G and divide it by minus NF. And for every term. And so delta G over minus NF, that's just E, the voltage. This is the standard voltage, E naught, and this will be minus RT over N times Faraday's constant times the natural log of Q. Okay, so in most applications this is room temperature. If it's not room temperature, then what different temperature will do is actually change the voltages. And so for example, pH meters, the voltage is usually calibrated for room temperature, but if you have a different temperature, some of them are sophisticated enough to actually correct for the changes in voltages and give you the correct pH, even if the temperature is not room temperature. There's the gas law constant, there's Faraday's constant. So we got two constants and something that is usually room temperature, 298 Kelvin. So what you might see is all of these collected into a single number. The other thing you might actually see is an equation with log, log base 10, rather than the natural log. And so the difference between natural log and log base 10 is 2.303. So we're going to take the gas law constant, 8.314, times 298 divided by 96,500 times 2.303, and want to get .0592 volts. Oops, I said it was log base 10 now. Log of Q. Okay, so why not natural log? I don't know, it's just more or less traditional to use the log base 10. This was probably back in the old days when they didn't even have calculators that do logarithms. You have to look up log tables, and they were all log 10. Okay, so let's do the example. Let's calculate the standard, not the standard voltage, but the voltage of a half cell, where we take copper 2 and reduce it with 1 electron to copper 1. The standard voltage is 0.153, so let's go ahead and substitute. Minus 0.0592 divided by N equals 1 times the log of Q. Now what is Q? Q is going to be the reaction quotient, so let's write that down. It's going to be the concentration of copper 1 divided by the concentration of copper 2. All right, so if the molarity of copper 1 is 0.045, this is 0.015, then it's 3 in this. Now let's calculate the numbers in this equation. So we're going to have the log of 3, which is 0.477, times minus 0.0592, And that's minus 0.028. Okay, the point I want to make is that since this 0.0592 is pretty small, and you're usually dividing by a number larger than 1, so this term is usually pretty small. So if Q is some very large or very small number, yes, this correction will be substantial, but usually if Q is somewhat moderate sized, this whole correction is going to be pretty small, and the best guess for the voltage is that it's going to be very close to the standard voltage.